Let's take a look at thermal image processing within Agisoft Metashape. Over the next two videos, I'm going to be taking a look at both radiometric and non-radiometric imagery. The first video covers images that are non-radiometric. And of course, what that means is that we don't have actual temperature values within these images, but temperatures are presented on the color scale. So usually a gray scale, where white would be the hottest and black would be the coldest within that image. And then we'll move on to the second video where we actually have radiometric data, so where the temperatures are included within those image datasets. Here I have 152 images from a FLIR camera, and each of these images, as you will see just now, is actually a double image, both a radiometric and a non-radiometric. So you begin by importing them into your project the same way you would for any image project within Metashape. So there's no difference from the outset. You'll see now, although I had 152 images, because of that double radiometric and non-radiometric, we suddenly have 304 total cameras. Now I have tried within Metashape, but for this FLIR system, regardless of whether we choose single cameras, a multi-camera system, or a dynamic scene, and we choose either of these options, none of them really gets the vision of the images the way I would like to see it. So I'm going to show you the process to divide them out as well. If you have a better way of doing it, by all means go ahead and do it. But for the moment, I'm just going to import them as we normally would. So what we then end up with is our 152 image placements, because each double image is captured simultaneously over the exact same position. And here at the bottom, when we look at the various images, we'll see, look at this first one. We have DJI 58, and then DJI 58 number 2, 59, 59 number 2, and so on. And if we have a look at the first image, which is the non-radiometric, just a grayscale image, we see the content of that image. And we look at the second one, and what we see there is really it's the same positions data. It just looks far more washed out. And we will look at the process of how we change the contrast of these images as well later on through the process. The first thing I want to do, however, is to separate the images out. So you'll see at the moment I just have a single chunk of all the images together. So what I'm going to do is go to my reference pane, and I'm going to run a little script that will select every second image. And it's a select every nth Python script. This is what it looks like. If you'd like to just take it down, use it for yourself. You have the option now to set the nth number to be whatever number you want to do. So every second, third, fourth, fifth, 50th, that's up to you. So within Metashape, we just say run script, we say OK, and here it gives us the option. So in this case, I only want to select every second image, and I say OK. And you'll see that's what it's done over here. So it has now selected every second image, those being the radiometric images. So the first thing I want to do is to actually disable them, because I'm going to do non-radiometric first. And I'm also going to just deselect them so that we know we're only dealing with the non-radiometric images. Before we carry on, something we always need to keep in mind when working with thermal imagery is that for whatever reason, the pixel size or pixel pitch doesn't come into Metashape very well. At least it doesn't with the FLIR cameras that I've worked with. So we go to Tools and Camera Calibration, and here we want to set that value, and this is the value I'm speaking about over here. So you'll see at the moment the focal length has been carried through, and it's making an assumption of a focal length of 947 over there. But when we correct the pixel pitch over here, which in this case happens to be 17 micron, and it's asking for this value in millimeters, so this is how we enter it. Correct that. You see suddenly it's changed to 529. So that is the correct value that we are looking for. And I'll do the same. So here, by the way, it has separated them out into the non-radiometric and the radiometric. That's why we have two different data sets. But we want to set this value to be the same for both. Obviously, this value is going to be dependent on the thermal sensor that you are using, as with the focal length. So just make sure you have the correct values, and it will translate into a focal length here at the bottom. Once that's all done, let's go ahead and save the project. What I would like to do now is to duplicate this chunk so that we have both the radiometric and non-radiometric in two separate projects. So we allow it to duplicate. So let's rename each of the chunks. The first one I'm going to just call grayscale, and that's the terminology I'll use for the rest of the video. And for the second, I'm going to name it radiometric. Of course, within the radiometric images, we want to select the radiometric now rather than the grayscale. So I'm going to run the script again just so that we can make that selection. And the first thing I want to do now is I want to enable these images and turn them on. But I'm going to invert the selection so that I can disable the non-radiometric. Actually, in this case, we may as well go and remove them now that we only have a single chunk, and we'll do the same for the grayscale chunk as well. Let's run that script so that we select only the radiometric in this case, and let's remove them as well. So now what we have is two very clean chunks, of the first being the grayscale and the second being the radiometric. The process now for alignment would be very much the same. However, what you'll find, because the pixel resolution is usually lower for thermal imagery, is that when we just use the standard high setting and the default 40,000, 4,000 setting for type point limit, it often doesn't find an adequate number of type points to align all of the images. So what I tend to do is go for the highest option over here and just really stick this number up to something quite ridiculous. It will never find this many images unless you're using an incredibly high spec thermal sensor. So don't worry that you're going to end up with too much data. And as you'll see, when we process, it processes very quickly. And just take note here of the 100,000, 25,000, because when we run this alignment, you'll see we get nowhere near. So we're finding about 5, 6, 7,000 points per image. But just this is real time that you're seeing on the screen at the moment. Note how rapid it is. So there's no real risk in this case of having too many points that your alignment is going to run for days and days, even when you have a very large data set. Of course, this is a small data set, but I would recommend fiddling with that setting at least to try and find more rather than fewer type points. So let's just wait for this to finish now. Now that it's finished, let's take a look at the result. So that's what we have. If we take it onto its side to look at how clean the data set is, really not too bad at all. I do want to go ahead and clean out these type points though as best we can. For no other reason, just that I like it looking neat and tidy. We know we don't plan on building models or point clouds necessarily, so this is less important than what it is for a RGB data set. All right, so that looks pretty good. Also run through the gradual selection steps. I'm only going to use the first two and not the projection accuracy, which I do use for RGB. So begin at reconstruction uncertainty. Just move this out of the way. I'm going to start at the value of about 10. Remember, we're aiming for somewhere in the region of about 10%. That's close enough over there, so I'm going to accept that, delete those points out, and optimize the cameras using the settings as they are. And we'll then run the second gradual selection step as well. Well, the first really. And we're going for a half pixel over here. Found another just over 10%. Optimize again. And that should be enough. So let's save the project over there. We then want to go ahead and create a surface onto which we can build our ortho mosaic. If you are, for whatever reason, creating point clouds or models of your thermal data, you can do that and then use those data sets as the base for your ortho mosaic. In this case, I'm just going to go ahead and create a dem, and I will rectify onto that. So I'm going to use the depth maps just to give us a higher resolution of dem. You'll see at the moment it's about 12.5 centimeters. I will leave the quality on high over here. If you run it yourself and you end up with worse results, you might want to adjust this value. But that really is going to be dependent on your situation. So let's let that run. Again, because the data sets are so small, you'll see that this is a very quick process. So once that's complete, we can go ahead and just take a look at our digital elevation model, make sure it looks somewhat sensible, and it does. So nothing wrong with that at all. It all looks to have worked out quite well. So the following step would be to build our ortho mosaic, and we're going to use the dem as the basis for that, or as the base for that. And this is something we're going to take a look at a little bit more when we get into the radiometric creation. But which form of mosaicing or blending is best for thermal data? For the sake of the grayscale image, I'm going to go ahead with the mosaic, the default option, and allow that to process. And then we should have our first result quite soon afterwards. So that too is a very quick process. And then we have the ortho mosaic created. Let's just turn off the background map. So this all looks pretty much how we've expected it to end up. So as we can see, there's a bit of shadowing behind each of these buildings, thermal shadowing. And that's because this data set was captured in the middle of the day, just a little before 2 p.m. Is up in the Northern Hemisphere in Switzerland. And so we see the shadows are quite long cast behind the images. But when we zoom in, let's look at the cars as an example and start to see some more detail. We can start to, very barely, but we can start to see what is hot and what is cold. So in this case, with the grayscale image, hotter regions would be lighter in color, and darker regions are going to be the colder areas, like we see with the shadow of the buildings as well. So something we can do to make this image a little easier to interpret is to now adjust our brightness and contrast settings. Let's give the automatic settings a go and see what it comes up with and take a look at the results. Okay, that's quite interesting. So now we can go in and we definitely are able to ascertain a bit more because of the high contrast result. And we can go in and we can see the various aspects within these images and what they have to tell us. But it doesn't end there. So it's not just the grayscale that we are dealing with. We have the option to edit the color palette somewhat. So we'll use the raster transform tool. And what we need to do here is tell it which band to use. So see, automatically it tries to determine which bands we're using. So it is the first band, B1, which is the long wave infrared. So we just want to select band 1 in this case, because if we don't select anything at all, we won't be able to apply a palette. So I'm just going to select band 1 with no formally following that and apply. And you'll see instantly it's gone all red and rather nasty with values on the left-hand side here that don't make much sense. But we then move on to the color palette, and we'll see we have 0 information here within this table. And so we just want to refresh our values and automatically scale them by hitting the refresh and auto button. And when we apply that, we can now view the data across this heat color palette. So we've got heat, we've got gray as well, but that should go back to what we saw earlier. So let's stay for a moment on the heat map, and I'll show you some of how we can investigate the image. At the moment, you'll see the blue or the cold areas are dominating. So we see the blue and then the red, which is the very hottest, but we're not able to determine much of what's going on these buildings as an example. So what you can do there is you can limit what we want to look at. So we know the blue is in the shadow, so let's pretend that for whatever the purpose of our project was, we weren't too interested in the colder values, so we can just move the scale bar some way out of the blue and apply the results. And instantly you see how we're able to determine more values. So we can shift it a little bit more. We apply that as well. And by doing so, we start to find a way in which we can scale what it is exactly that we are looking for. You can also just enter the values over here and apply them. And when we do that, you see it works much the same way as dragging that scale bar across. So if you know there's a region of particular interest, you can tailor this graph to exactly what you are wanting to see and wanting to determine. And that's pretty much all you're able to do with a grayscale thermal image within Metashape. There are options, of course, when you export this out to a third-party tool such as QGIS, ArcGIS, and Global Mapper to do some further analysis. So let's take a look at that. So I'm going to export the Author Mosaic, and I'm just going to call it grayscale image. And here we have a few options. Just for the sake of making it easier to work with, I am going to export it in its UTM zone. And here with thermal imagery, this is something you won't get on your standard RGB imagery, is your raster transformation. So do we want to export the index color or the index value? If you export the index color, you will export the image exactly as you see it here on the screen. So however you may have adjusted that raster transformation template, you would export that image. But if you want to perform some amount of analysis, we could then go and use the index value, and we're going to export that. Before I export it, just to tell you what the index value is as I move the mouse across the image now, you'll see what's going on here in the bottom right-hand side. You'll see a value, an index value over there. So that is the index value that it is speaking about in this case. And it will be a value, I think, from 0 to 256. So your standard 8-bit range over there. So let's export this Author Mosaic. Remember, we're just calling it grayscale for the sake of simplicity. And I am going to export the index value. And let's make sure we are using the UTM-32. And we'll export that. We can then take that image now and open it up in another piece of software. So in this case, I'm going to use Global Mapper, just my tool of choice. And you'll see what I've set Global Mapper up to do is to read those indices or those index values as elevations. So they're not really elevations, but if you have a look at the bottom left-hand side, as I move the cursor over the image, it's telling us a height. So it's not a height, this is not an elevation, it is that index value. And here it is, we've got the Celsius symbol here, but it isn't Celsius, so just keep in mind this is a pure index value. And we can change that, of course, so that it's not confusing once you deliver data to a client. But what we can do is we can then change within Global Mapper, and again, you could do this in QGIS and ArcGIS or whatever your tool of preference is. We can change the palette we want to use. So I'm going to use a color ramp shader. And this is very similar to what we saw just now within Metashape as well. I have made a custom one which represents what Pix4D does, which gives us something like that. So it's a nicer way of being able to interpret what values we have. And we can see far more detail here. Just as an example, zooming in on the cars now, we're able to actually determine which vehicles might have been parked for longer or in shadow for longer. You can see this car as an example. The top end where the bonnet is colder than the back end. The sun is obviously on there. But if you have a look at this one, here we see the engine bay here on the bottom, and it's hotter than the rest of the vehicle around. So perhaps that car hasn't parked too long ago. Same with this one over here. What we can also do with this, because we've imported it as a pseudo height value, is we can alter the elevation value, so alter the range that we're looking at. So let's pretend that we want to start at 100 as an example and apply. And you'll see how we now start to scale the image a bit more by doing that. What you are able to do though within a tool such as Global Mapper is allow it to just scale the images based on what you have on screen at the moment. So you'll see, as an example, the top of this building is covered for the most part in oranges and reds. But if we zoom in just to that building roof as well, we zoom in a bit more, we'll see a greater color spectrum coming for just this region. And that's because if you look at the scale bar here, it's ranging only from 75 to 170 or so degrees at the moment. So this is just an illustration of what more you can do when you export a grayscale thermal image out of Metashape and into a third-party tool. It gives you far more options, and at least over here as well, we're able now to tell far more easily what is hot being black, blue, purple, versus what, pardon me, it's the other way around, what is cold being the black, blue, purple, and then what is hot being the whites, the yellows, and some of the reds as well. And that covers the non-radiometric or grayscale thermal image processing. Of course, within Metashape, if you were not pleased with the results, and something you will find with all thermal imagery is that your DEM isn't always ideal. So if you do have a DEM that was produced using RGB imagery, or if you have a third-party DEM that you would like to use, by all means go and import that and use that as your rectification surface. One of the reasons I'll show you over here is just using this building as an example. You see the messy edges we've got on this building. If I go back to my elevation model, you see what I'm talking about over here. One way to get around this would be to take the longer process and build a point cloud I found, and then a 2.5D model from the point cloud, and that will give you much cleaner results. So it's just the standard build point cloud, clean up your point cloud, and then build a model based on that point cloud, selecting the 2.5D option. In the next video, we're going to take a look at the radiometric processing. So that goes into a bit more depth now on how we actually interpret those temperature values, what other data and meaning can be extracted from the images, and we will take a look at FLIR tools as well. Thanks for watching.